Okay, so this is the sixth set of asynchronous material for the stats to help out the summer, and this time we are taking up what do you call it? Continuous probability distributions. So last time around we did probability distributions that were discrete, which led us to the binomial distribution and the Poisson distribution. This time we're taking on things that are continuous in nature, and these are given usually by what's called a probability density function. So what you're dealing with here is you get some function, we'll call it f, and it's given over some usually closed interval like a to b. It can be from negative to infinity to positive infinity. Like the normal curve is a probability density function that goes from negative infinity to positive infinity. But it doesn't have to be. It can be over a closed interval. The key here is that if I graph this function f, right, over its domain, a to b, so here's my function f, the area under the curve and above the x-axis, so those of you who are in calculus land, the integral from a to b of f of x dx will equal 1. Okay, so if you look at the notes, I gave you a pretty simple example of this. This negative half x plus 1 on the interval from 0 to 2. So it would be this region here, right? If I'd found the area of that region, that's a triangle. So that's half its base times its height, which gives me an area of 1. So this could be an example of a probability distribution function. Probability density function over that region. So what I did here is I said, okay, so how does this work? So if I put 0.5 here and 1 here, then the area of this is going to be the probability from 0.5 to 1. So it's the probability that the random variable takes a value between 0.5 and 1. So here that's a trapezoid. So the area of that region is going to be half base 1, which is 0.75, plus base 2, which is 0.5, right, times its width, which is 0.5, which I believe comes out as 0.3125. So the probability that my random variable would take a value between 1/2 and 1 is 31 1/4%, right? Now, the idea here is that no particular value, the probability of it taking any particular value is 0. Okay, so like this is like things like weight and height and things that are continuous variables. So like the probability that you actually weigh, 175 pounds exactly is 0. Nobody actually weighs 175 pounds exactly. You're always a little bit more or a little bit less than that by some amount. So given that there's a lack of precision there, you're going to say, okay, the probability that somebody weighs between 175 and 200 is this. Okay, so that's a pretty basic idea of how a probability a probability density function can give a continuous probability distribution. So we can find out the given probability for any given interval if we have the probability density function. All right, so it makes a small tie to calculus there, things like this. The basic easiest idea here is the uniform distribution, and this is where like every interval of the same size has an equal probability of occurring. Okay, so like things actually happen randomly. So let's say I have some interval and there's time 0 to time 10, right? So let's say that this is a 10-minute interval and a train can arrive at any time in that 10-minute interval with an equal likelihood. This is a uniformly distributed problem. So we create this number, we're going to call it B, and B is the maximum of the interval minus the minimum of the interval, which means here B is 10, which means that the probability density function for this interval is 1/10. So this is the f of x, it's a constant where f of x is equal to 1/10. Now, the only part of the domain we care about is from 0 to 10, right? So if you do a little bit of math here, if I take 10 times 1/10, the area under this curve is going to be 1. So it can serve as a probability density function. And let's say I want the probability to be that like you arrive at, time 0. What's the probability that you're going to be waiting more than, let's say, 7 minutes, right? So that's asking, like, what's the probability that the train's going to arrive between the 7th minute mark and the 10th minute mark? So that would be the area under the curve, right? So the width here is 3. The height here is 1/10, which means that the area of that is 3/10, which makes logical sense, right? That, 30% of the time you would have to wait more than 7 minutes if it's guaranteed to arrive between 0 and 10 minutes and you are arriving at time t equals 0, right? So that's like the basic continuous probability distribution. The one that is the most common continuous probability distribution is the normal curve, right? So we're actually going to see another curve a little bit later on here, which is a thing called the t-curve, which was invented in order to do inferential statistics on means when you don't know the standard deviation of the population, but we'll get into that next time, okay? So this one is like things that are distributed in this bell-shaped and symmetric way. Okay, the domain of this thing is -infinity to infinity. Okay, so we have a standard normal curve. The standard normal curve makes the mean of the curve equal to 0 and makes the standard deviation of 1. Okay, so it's bell-shaped and symmetric with a mean of 0 and a standard deviation of 1. This is the probability density function. It's ugly. It has like pi's in it and e's in it and things like this, but you'll notice in there that there's one variable, x, and there's two parameters, because there's like a constant e and a constant pi here, but there's two parameters. The parameter is the mean, and the other parameter is the standard deviation. And if you make the mean 0 and the standard deviation 1, this thing gets reduced down to like e to the -½ times x squared over square root of 2 pi, which is like the simplest version of this curve. But when you control those two parameters, everything else gets controlled. All right. So the key here is like using this thing with the TI-84. All right, so let's say I'm in a standard normal situation and I want to know, like, if my score is between -1 and 1, what's the probability that I'm going to get a score between these two things, right? So I want the area under this curve. That's what I'm going to try to find. Now, calculus, you would throw this thing into an integral and find the integral from -1 to 1 dx would give you this answer. Stat students don't take calc usually or before they take this course, so we kind of hand wave at that a little bit. So what we're going to do is we're going to grab the calculator here, and this function is actually built in. So I'm going to clear everything out here, so I'm starting fresh. There's probably some earlier work in there. All right, so I go second vars. That gives me the list of distributions. I'm going to use the normal cumulative distribution function, okay? Not the PDF, but the CDF, right? So I want the probability between two values. Okay, so for my lower bound, I'm putting in that -1. The upper bound, I'm putting in 1. This is a standard normal curve, mean of 0, standard deviation of 1. And I hit paste, and I get 0.682. So the probability that my random variable is between 1 and -1 is 0.6827-ish. Okay, now, this makes a connection. Because remember, we said that the area under the curve between the first standard deviations was about 68% when we did the empirical rule, right? It's about 68%. So like just following this out, if I make this -2 to 2 and play that out, there's the 95% for the second part of the empirical rule. And if I go -3 to 3, that's going to give me the 99.7% for the third part of the empirical rule. So this is where that 68, 95, 99.7 comes from in the empirical rule. But this is like a much more formal answer to that. All right, so what you're picking up on here is that in the normal curve, you're literally creating a standard or a distribution of z-scores, right? So this is the probability that my z-score is between -1 and 1, because the z-score is how many standard deviations am I from the mean. Okay, so like things don't normally have a mean of 0 and a standard deviation of 1, and the standard normal just really gives you a distribution of z-scores. And back in the day, what you would do is you would normalize all your scores to z-scores, and then you would find your probability. So like, let me show you how this was done, like in the day when we had tables and not these sophisticated calculators. So you can see like kind of how we've grown up a little bit here and make the connection to this reality. So let's look at something that's not standard, right? So IQ is usually the classic example of having a mean of 100 and a standard deviation of 15, right? So back in the day, if I wanted to find the probability of having an IQ score between 80 and 90, right? So that's like down here, 80 and 90. What I would do is I would first find the z-scores. So the z for 80 would have been 80 minus 100 over 15, which works out to be like -4/3, right? And the z for 90 gives me 90 minus 100 over 15, which comes out as negative 2/3, right? So literally what you would have had to do is that the old school tables actually gave you a graph that looked like this. And it said, okay, here's the z-score. And it would give you a drawing that said, okay, this was the value up to there. And the table would say, okay, if you knew the z-score, what's the probability that x is below that value, right? X is below the z. So you would find the probability that x was below negative 2/3, and you would find the probability that x was below negative 4/3 in the table, right? And then you would subtract these, because this would be the curve, right, below negative 2/3, and then this would be the piece below negative 4/3. And when you subtract these two things, you would get this region here. So this is like how we used to do this. You'd have to go and you'd have to turn it all into two z-scores. And then you would find the probability below one z-score and then the probability below the other z-score, and you would subtract them. Okay, like you can even do the standard normal thing here for these two z-scores and get the correct answer. You second vars normal CDF, and we want to go negative 4/3. Sorry, no, the lower bound's negative 4/3 to negative 2/3, right? And thirds. And we're going to keep it as mean of 0, standard deviation of 1. And it's going to tell me that that's 0.1613, right? So 0.1613 is the probability that my z-score is between negative 2/3 and negative 4/3, which is the same as my probability under mean of 100, standard deviation of 15, that I'm between 80 and 90, okay? But these wonderful people from Texas Instruments like don't even want me to do that much work. I can literally just feed into the calculator the normal CDF from 80 to 90 with a mean of 100 and a standard deviation of 15, and voila, there's the 0.1613. So yeah, there's like, these tables are still in the textbooks and all of that, but really nobody's using them in practice. You might get somewhere an old school professor who's been teaching the same course for 20 years who's like, I'm going to make them learn how to do this with a table, but it's really just not practical. So if you have a curve that's either standard normal or just a normal curve with a given mean and standard deviation, you can literally feed these values into the calculator and come out with the given results. So there you have it. It's pretty simple, straightforward, not entirely difficult to deal with. So I walked through that in the notes. I walked through it with the standard normal and then just letting the calculator do the heavy lift. And you see it results in the same value both ways. All right, so finding this backward is an interesting question, okay? So like inverting this entire process. So what if I know that like, all right, mean of 0, standard deviation of 1, and my z-score, I want to know what z-score gives me 75% of the curve below me, right? So what z-score is the same as the 75th percentile? So Now remember, this is not unique, right? There could be more than one value that could serve as the 75th percentile. It just has to be in such a way that 75% of the population is below you. So like what z-score could serve as this, right? So I want to inverse this process. Okay. Now, back in the day when you did tables, you'd have to go find the 0.75 in the table and then work backward to figure out the z that got you that 0.75. Okay? It's inverting the normal curve is literally what you're doing there, right? So this is actually also built into the calculator. So if I go second vars, option number 3 is the inverse norm function. So I want the area to the left of my mark to be 75%, right? And I want the z-score that corresponds to that, so that's a distribution with a mean of 0 and a standard deviation of 1, which means that if I have a z-score of 0.674, right, then 675, because I should probably round up there, then I know that 75% of my population is below my score. At least 75% is below that score. So this would be a good stand-in for the 75th percentile, right? This is the same as Q3, right? 50th percentile, 75th, there you go. That's Q3. So there you go. That's using standard normal, but again, nothing in the real world is distributed with a mean of 0 or a standard deviation of 1. So back to my IQ question, right? Oops, sorry. That jumped around. I was on the wrong page. Back to my IQ question here, right? So let's say I'm in the IQ situation where mean is not 0, but mean is 100, right? So mean is 100. Standard deviation is 15. And I want the IQ score that is the 85th percentile, right? So I want to know what IQ score do I need to have to know that I'm doing better than 85% of the population, right? So this is pretty simple. I go in, I go second vars, invert the norm. I want the area to the left of my value to be 85%, the mean to be 100 with a standard deviation of 15. Hit paste, I hit enter, and it tells me that if I have an IQ score of 115.6, right, rounding up, I would definitely be better than 85% of the people in the world, right, or in my population. So there you go, inverting the norm with a non-standard normal curve. Not so bad. All right, this brings us to what is probably one of the more challenging ideas for students to get, which is sampling distributions. Okay, so I have some population, and I'm going to take a sample of that population of size n. Now, I'm going to measure that sample, and I'm either going to take a quantitative measure or I'm going to take a qualitative measure. Okay. Quantitative is going to yield a number. Qualitative is going to yield something that's non-numeric, right? When I take these samples, that quantitative group, I can actually take the mean value of the samples. So like, let's say I take a sample of people, I grab their height, I can find the mean value of the height. Okay? If I take a sample of people and I take their age, I can find the mean value of their age. Okay? Quantitative, I can take a mean. So quantitative is mean. All right, qualitative, you cannot take a mean of blue. It doesn't make sense to do that, right? So we're taking people that have a certain quality. So like the quality might be favorite color is blue, right? So the way that I get a quantity out of a quality is I take the proportion of the population. So we're going to use P for that, right? So qualitative is going to yield a P, right? So P is going to be the proportion of the population that has that quality. All right. So this is going to yield a mean of the sample. This is going to yield a proportion of a sample. So mean of a sample is X bar, proportion of a sample is P hat. So this is read as X bar. This is read as P hat, right? And here's the thing. Under certain conditions, if you take enough of these samples, these values will be distributed normally as a bell curve. Okay, so this is the weird part. So I'm going to sample these things, right? I'm going to take samples of size n, and I'm going to take a whole bunch of those samples. And if I start mapping out those samples of size n, if it's a quantitative sample, the mean of those samples are going to be normally distributed. Or if it's a qualitative sample, the proportion of those samples will be normally distributed. Now, the first thing is like, under what conditions does this happen? And like, okay, and then once I have those conditions, what are the parameters of the normal distribution? So what are the mean and the standard deviation for this curve? Okay, so that's like what's going on with sample distributions. So you're taking samples all of the same size. You're taking a mess of them. And you're either looking at the mean value of a quantitative sample or you're looking at the proportion of a qualitative sample. And then as you look at all of those mean values of the samples or all the proportions of the samples under certain conditions, which we're going to get into, what are those conditions? Those sample distributions will be normally distributed with a calculatable mean and a calculatable standard deviation. Okay, so I'm going to pause just for a second, let that all sink in. If you got to go back and listen to that again, it's worth doing because this is where kids get tripped up because you're taking a mean of means and a mean of proportions, a standard deviation of means, and a standard deviation of proportions. And this is what sampling distributions are. Very challenging. Okay, so the part of this that we have to answer first is the under what conditions. Okay, so what you've got to notice is that we are creating a situation that has central tendency out of something that may not have central tendency. So there is no requirement that the population has to have central tendency. Because, I mean, in all honesty, we may be measuring something that is qualitative here, right? I don't know how to measure the center of what is your favorite color. That doesn't make sense. So what we're going to do is we're going to use an idea that creates and evokes central tendency where central tendency might not actually exist in the population. And we do this by using repetitive sampling. Okay, so this brings us to a thing that's called the central limit theorem. Now, proving this is something that is like way deep into theoretical statistics. We're not doing that here. We're going to posit it and we're going to accept it. Central limit theorem says that your sampling distribution will be normal with certain parameters, right? If one of two things is in place. Either A, the population is measured using a quantitative measure, and the population itself is normally distributed. If you've got that, you're good. Then we know that the sample distribution is going to be normally distributed with a certain parameters for the mean and the standard deviation for the sample distribution. The other option is B. The samples that you take, right, are sufficiently large. And usually that the samples of the population only have to be about size 30 or bigger. If I've met either A or B, then I get a sample distribution that is normal with certain parameters of mean and standard deviation. Now, that feels kind of like magical. That I can take something that is completely not normally distributed. I can take samples of a particular size that's bigger than 30 and end up with a distribution, a sampling distribution that is normally distributed. That is bell-shaped, symmetric around a particular mean with a particular standard deviation. That's where like the magic of statistics happens. This is the big theorem that allows us to draw inferences in statistics, is that we can get centrality and normalcy when none exists in the population. All right, so if I've not sounded excited enough, this is a really big deal. So what we need to do is we need to look at what does this look like in reality. So we've answered the first question. What are the conditions that we have to have? Either the population has to be normally distributed or the sample sizes have to be significant, larger, 30 or larger, right? If I have that, then I've got central limit is in play and I'm good to go. The back end of this is now that I know that my sampling distributions are normal, what is the mean of the sampling distribution and what is its standard deviation? Okay, so typically when we are in the quantitative case, what we're going to do is we're going to take a measure of all the things in the sample, and then we're going to take the mean of those measurements. So you're going to get a sample mean, right? So you're going to get a sample mean for each of the samples. Now, if you take all of those samples together, those means are going to be normally distributed, and the mean of the sample means is actually going to be equal to the mean of the population. So the way you read this sentence is to say that mu sub x bar is equal to mu, or the mean of the sample means is equal to the mean value of the population. Even if the population is not normally distributed, that will still hold. Okay, the standard deviation of the sample means, if central tendency or central limit theorem is in play, is going to equal to the standard deviation of the population times the square root of the size of each of those samples. Okay, so this usually is like where people are like checking out. They're like, what the heck is going on here? And what you really need to do is to kind of put this into something that makes like real world sense. So let's create a quantitative situation. Okay, so this is a known reality that on average, so the mean of the population is on average, a pregnancy lasts 268 days. And these happen to be normally distributed with a standard deviation of 15 days. Now, right there, not saying anything else, not even knowing the sample size of the samples that I'm going to take, I have met the central limit theorem because I have a quantitative population that's normally distributed. Okay, mean of 268 with a standard deviation of 15. Now, that doesn't have to be the case. I just have to have a mean and standard deviation. It doesn't have to be normally distributed. And I could still do this so long as the samples that I'm taking are of the right size. So what I'm going to do is I'm going to start grabbing babies at random. Okay, and I'm going to grab 100 of them. I'm going to say, how long was the pregnancy for that baby? How long was the pregnancy for the baby? How long was the pregnancy for the baby? 100 times. Okay, and then I'm going to take the mean of those 100. Okay, now, that's what I'm going to do. Now, I'm going to do those samples of size 100 over and over and over and over and over again. I'm going to see what happens. And what I'm going to get is I'm going to get that those means that I get from those samples of size 100 actually fall on a bell curve. And not surprisingly, the mean of those sample means happens to be the same as the mean of the population. It happens to be 268 days. Now, if I take all of those means from the samples and I look at that bell curve, its standard deviation is going to be 15 over the square root of the sample size 100, which is 1.5. Which means that if I keep sampling this population over and over and over, again, I'm grabbing 100 people at a time, and I take the mean length of those pregnancies, those results are going to have a mean of 268 with a standard deviation of 1.5. which means that like if I go out to the 2 standard deviations here, right? So if I play my what do you call it? My range rule of thumb, 4 standard deviations, 2 in each direction. So this one should be 268 minus 2 times 1.5, which puts me at 265. This one should be 268 plus 2 times 1.5, which is going to be 271. Okay. This means that if I grab 100 people, 100 babies at random, a normal sample is going to have the mean number of days that those babies were in the womb for is going to be between 265 and 271. That doesn't mean that the average baby is between 265 and 271. It means that the average of 100 babies is between 265 and 271. And anything beyond that is an unusual sample. Okay, it's either got too many that are way too long or too many that are way too short. It's an unusual sample. Now, if you notice, this is a really tight interval. This thing only has a difference of 6 days. Okay, so this means that like I can tell if a population is weird by just grabbing 100 people of it, right? And saying, woo, wait, I came up with something that was like way outside of this, right? Something's not right here, okay? So if a sample is outside of this by a lot, something's weird about that sample. Okay, so this is like the power of statistics. The average baby is using 268 and 15, right? So that means that the average baby is going to be somewhere between 238 and 298. But the average of 100 babies is going to be between 265 and 271. This is why, like, there was an experiment that was done way back in the day, okay, where at a state fair somewhere, or actually I think it was a world, might have been a world fair, it's something, big fair, right? They went and took a cow. And they put that cow in the middle of the fairground. And they had people try to guess the weight of the cow. Okay? Now, here's what ends up happening. You have guesses and guesses and guesses and guesses. And when they took the mean of that sample, right? So here you go. The mean of the sample, right? The mean of that sample should be somewhere between the mean of the sample should be on a distribution that's centered around the mean of the population, right? The standard deviation of that sample should be the standard deviation of the population divided by the square root of the sample, right? So now think about this. The mean of this sample, of the distribution of these samples, should be somewhere centered on the mean of, like, the guesses. So that's actually the cow's weight, right? So these samples should be centered on the cow's actual weight. And then note the sample size as it's increasing is making this standard deviation really, really, really tiny, which means that whatever distribution this is going to be, the standard deviation of those means is going to be small, which means that pretty much if you let this go on for the length of that fair and you take the mean of the guesses of that cow's weight, it's pretty much going to hit the weight of the cow, plus or minus probably within a pound. It's a neat little statistical trick, but it's based on what we just did. Okay, so in the end, it's a neat little game that you can play. You can like put a thing of jelly beans out there, and people are gonna wildly guess at it. Some are gonna be like way too big, and you're gonna take way too small. But if you add up all of those guesses, and then you take the mean of those guesses, as long as you have more than 30 or so guesses in the thing, you're gonna get a result that's kind of close to the actual number of jelly beans that's in that jar. So, yeah, this is why things like markets are rational and things like this, because people can guess really badly on stocks, but on average, they hit the value dead on and things like that. So, this is like a pretty powerful kind of thing. It seems like almost like hocus pocus, but there's a lot of reality that drives why this works. So the case that's a little less clear, and it seems even more like foggy to people, is how to deal with a proportion. And this is the one that comes up in politics. So this is like your qualitative situation. All right, so the example that I used here was that the quality was believes country is COUNTR moving in the right direction, right? So the country's getting better, right? So let's say in the actual population, the proportion of people that believe that the country is moving in the right direction is 35%. Now note, population only has one parameter here. No mean, no standard deviation. This thing is not at all like, what do you call it? Meaningful, right? So the question here is like, how do I meet the central limit there? Well, I have to have significant sample size. So I need to take samples of larger than 30. So like in my example here, I took sample sizes of 100 because it's easy to work with because the square root of 100 is 10. Okay. So what happens here is that you end up with p hat, which is the proportion of the sample, right? So P is the proportion of the population, P hat is the proportion of the sample. This is going to be normally distributed with the mean of the P hats is actually going to be equal to the actual portion of the population, and the standard deviation of the P hats, and this takes a little bit of mathing to get at, is P times Q over N, take the square root. Remember that Q is equal to 1 minus P. Okay, that one, not intuitive, okay? You could do some work to get to it. We generally just take it as something that's accepted, but it does actually work out. So like looking in my example here, what I'm saying here is if I start taking these samples of size 100 over and over and over again from this population where 35% of the people think the country is getting better, I'm going to get samples that are distributed with a mean around the proportion of the population, 0.35, with a standard deviation being the square root of 0.35, right? 0.35, okay, 0.35 times 0.65 over the size of the sample, 100. Okay, so in this example, right, that comes out to, I believe, 0.0477. So this means that the samples that I'm getting should be 0.35 minus 2 times 0.0477 on through 0.35 plus 2 times 0.0477, which means that they should be somewhere between 0.2546 and 0.4454, which means like 25.5% of the sample should say between 25.5% and between like 44.5% of the sample should be saying, hey, I believe that the country is going in the right direction. Which, like, because the sample sizes are 100, that's literally between 26 and 44 people, right? So if I took a sample that was like 80 out of 100 people said that the country is going in the right direction, then something's not right here. Either that sample is not representative of the population, or my understanding of this population is wrong. And that's what's going to bring us into hypothesis testing, is this idea that the sample should lie in a certain range, and either it does or it doesn't. So kind of giving you a taste of what's going to come here, kind of follow this out. What we just said was, I believe, that the population has 35%, right? And somebody else comes in and goes, no, 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 no. I think this is much higher, right? So we go and we take a sample. And in that sample, we find that 80% of the people actually said the country's going in the right direction. Okay. And this sample was a simple, random sample of the population. Okay. So what should happen is I should be between 0.25, right? I think we just said, and 0.45, and it's not. So if this is true, then my sample within 2 standard deviations should be here, which means like I'm 0.68% confident that I should be here, right? Well, it's not. It's like way out at 80. So what if I make this like 95% confident, right? So I'm at 3 standard deviations. So let's see what that would be, right? So 0.35 minus 3 times 0.0477. Let's see, that's 21%, right? 0.35 plus this, right? Should be like 50%, right? But no, I got a sample that was 80. 80 is nowhere near then. This is like 95% confident. I'm saying with 95% confidence that if this is true, then my sample 95% of the time should be coming up between 0.21 and 0.5. But I got a sample that's at 0.8. So what do? I reject this. I say there's no way that this could be true, right? Which is lending evidence to saying this. It supports this claim that the population is actually bigger. Okay, so this, like, if I got, if I said, oh, it's 0.35 and I got like 0.49, well, that's still in that interval. So I fail to reject this. I say, okay, that's okay. But here, what I've got is like something that's way out of the bounds. So I say, okay, I'm going to reject this, and it's going to support the other claim. This is what we're going to pick up in the last video, is how to formalize all this. Because we've got all the moving pieces to actually be able to draw inferences, to test a hypothesis and say, okay, that hypothesis is true or it's false, well, we don't say that it's true. We say that we can accept it with a certain degree of confidence, and or we say that, we reject it. But we're going to look at that next time around. But you could see at this point, once we have the sample distributions in play, this leads us indirectly to that hypothesis testing, which is like the bread and butter of statistics. And once we have that, we have the whole shebang. So I hope you can see how we went from descriptive through probability to get to probability distributions, and then creating sample distributions by using sampling, which was stuff we learned on the very, very first day of all of this. And then once we get that together, we can start testing hypothesis and drawing inferences, which is where like everything comes together. So I don't know. I hope you think it's like magic like I do, but it's kind of cool stuff. All right. So that's 6 for 7, and we're getting there. Thank you.